here. Yeah, welcome everybody to the Tuesday Tech Talk for EECS. This is the third of the season, so we have these bi-weekly. And this quarter, we always try to have a theme for the quarter, and this quarter the theme is new to EECS. So we're talking to the new faculty that we recruited last recruiting season, and they're starting up now. So really it's exciting. I'm hoping we can do this every year. We're growing so fast, we're gonna have to be hiring like crazy. So might just be a fall tradition, we'll see. But today we have Sibin Mohan, who's coming to us with an unusual amount of experience for a new faculty. So he's most recently, he was a research assistant professor at Illinois, Urbana-Champaign, and worked there for a while, doing a lot of research, advising students, doing just what a normal professor would do. So he's going to be coming in, with lots of experience. We're excited. He's one of our newest security faculty, and this is particularly exciting. I remember back when I first arrived, there was a strategy to grow the AI group. I was like the third person, and we can continue growing. And today we have an AI graduate degree, lots of work going on in AI, very exciting. And some number of years ago, we decided to do the same thing with security, and we can sort of see that working out now, where we've got great additions, including Sibin, this year. So it's going to be exciting to see how this security group at OSU evolves. And I think, Sibin's done all sorts of interesting things in security. I think he's kind of a jack of all trades. I wouldn't be able to name all of the things, but he does IoT, he does autonomous systems, and you name it. And today he's going to be talking about bloat in operating systems and how to get rid of it for security reasons. And that sounds like a good thing to get rid of. So I'm going to let you take over. So I'll just remind people this is going to be recorded, and it's being recorded now. You can ask questions through chat, or you can unmute and ask a question during the talk, and there'll be plenty of time for questions at the end. So with that, take it away, Sibin.
Thanks, Alan. Thanks for the great introduction, and also for inviting me for this talk series. I'm excited to be here on the campus finally. Today, I'm talking about methods to remove code bloat in contemporary systems, especially operating systems. And I'm going to be touching about two different techniques that we worked on. The second one is actually actively have been working with OSU faculty for the last couple of years. So feel free to stop me at any point if you have any questions. I may not be able to check the chat window regularly because I'm trying to minimize that to see my screen better, but feel free to just interrupt me and ask me any questions. So so if you look at a contemporary operating system, let's say Linux, and you look at the amount of code that's been added to it over the years, if you see, current versions of Linux are touching 20 million lines of code or more. And so, you think, oh, that's great. Like Linux has all this functionality, it supports all this hardware. What's the problem, right? The problem with OS code getting bloated is that there can be a lot of issues that show up. You have a lot of legacy code and dead code and driver code and so on that just stays on in the kernel. And the important thing to know is that most applications don't need all of this kernel functionality. So then why have this code? I mean, this code can lead to serious problems, as I'll tell you. If you look at a modern Linux version, it has 300 plus system calls that are implemented. And if you look at many popular applications like Apache or JPEG or gzip and Redis, they're using like a fraction of those system calls. So it's not that an application or even groups of applications need all of the functionality that's available in the Linux kernel at any point in time, right? At any single point in time. And even the text section of the operating system code is like 8 megabytes, but we notice that most applications use less than 10% of that. So a lot of the code just remains unused. Why do we care? Well, with unused code and with a lot of code that's not usually used by applications or exercised by applications, you can see increased attack surfaces. There's more entry points for attackers to get in. Also results in more faults and bugs, right? Like you have poor isolation as it is with kernel and applications. And so, with the larger attack surfaces and more potential for bugs, which is essentially the result of excess code, you have poor isolation. And so if an attacker takes control of the OS using some of these entry vectors, then all applications are vulnerable. It doesn't matter if your application was the one that caused the problem, but every application potentially becomes vulnerable. So what are we looking at? We're talking about this notion of debloating OS code. So at the high level, what I'm saying is, if you're given an application and its expected or known workloads, can we reduce the kernel footprint for that application? So the goals at the high level are, we want to reduce these attack surfaces, as I mentioned. We want to make sure we do this with minimum performance impact for applications. And we essentially want to get rid of the vulnerabilities and potential zero-day bugs. So how do we achieve all of this while still reducing code bloat? The whole point then becomes that if you're able to meet all of these goals, we say that the system is more resilient to attacks, more resilient to failures, easier to restart when a failure happens, and so on. But it's not that simple, right? I mean, code in operating systems exists for a reason, and operating systems are extremely complex pieces of software. The problems are that it's really hard to track which parts of the kernel is used by an application exactly. And then from that, trying to extract only the quote unquote necessary parts is also hard. I mean, we shouldn't, in the process of debloating code, actually break the system ourselves. We shouldn't make the operating systems unstable. And this goes back to the notion of complexity, right? The other part is that we need to know what happens during boot. At boot times, a lot of the choices of what code is loaded for what kinds of hardware and what kind of configurations is made at boot time. So if you don't have visibility into boot, then you're missing an opportunity to reduce this excess bloat. Again, it goes back to the complexity of operating systems. Boot processes have also become very complex of late. And we cannot be slow. I mean, the point is, okay, we can analyze the system, we can take our sweet time, we can say, oh, we will come up with great processes to remove the bloat. But you sometimes on cloud systems and even other applications like IoT or edge computing systems, you want to do fast application deployment. So you can't really slow things down while you take your sweet time to analyze the whole system and to build debloated kernels. So there are a lot of challenges, technical and engineering challenges that show up while we're trying to do this. So today, like I said, I'll present two techniques that we've worked on or developed over the last few years on how to debloat kernel code. And they're very different philosophies. On the one hand, we use what are called configuration-based debloating, which is coarse-grained, which is where we may not have complete knowledge of all the application workloads. It's targeted for a single application. It has higher stability overall, right? And on the we call this tool framework COZART. On the other hand, we can use more dynamic or trace-based methods that gives us more fine-grained control of how much code to remove and where. We can do this if we know the application workloads are very well defined. We might even be able to orchestrate multiple applications, and I'll explain that in a bit. But the problem is that with the aggressive debloating, there's such problems with stability as well. So we'll have to address that at some point. And this framework is called multi-K. So I'll start with COZART. COZART stands for Configuration Mozart. It's a name my student thought was really pretty funny. So he's like, we'll just make that. It's a framework for debloating operating system kernels using what are known as configuration options. What are kernel configurations, right? So kernels, as with most code, have configuration options that are compile time options. What do I mean by that? So these could be like, these preprocessor hash ifs that you find at the statement level around certain statements, or even around certain functions. And these are the code preprocessor statements that we can fine tune. On the other hand, you can look at make files and see that they have object file configuration statements as well that you can define either from configuration files or the command configuration scripts or the command line. So these are also things that we can fine tune help us reduce the code bloat. So different operating systems have various ways of dealing with such configurations. Linux and L4 use kconfig, FreeBSD uses a key value format, and other operating systems have their own methods. So we want to use these kernel configurations and understand at compile time what parts of the kernel are used, and then actively use the existing configuration systems to help reduce or remove code. The problem is, as it stands today, these kernel configurations are not the best things for code reduction. They're used for other things, for optimizing things like hardware configurations or library support or dependencies and so on, but not for reducing code. And the problem is, even these systems are increasing in complexity every year. I mean, if you look at it, there are like hundreds or even thousands of new configuration options added every year. I mean, kconfig at this point has like 18 or just under 18,000 or so configuration options. Also, this number is a year or two old, so there might be even more now. So this is, just because we have this ability doesn't mean that we can use it directly for what we want to do, which is getting rid of the code, excess code. So let's talk about COZART first. So it's an advanced operating system debloating framework, which is automatic and transparent to the end user. So application developers don't have to realize you're doing anything. You don't need to recompile the system. It's also automatic, so there's no manual intervention required. And there are some properties we wanted to integrate into COZART, which is that one is it needs to be composable and reusable. It needs to support fast deployment. We need to have better visibility into the whole lifetime of the application and OS, which is including those boot times. And we want to track these configuration options at a very fine-grained level. So we developed this notion of configlets, which are essentially, there are two kinds of configlets. The first one are baselets, which are configuration options that are specific to the environment, which is whether you're running on a VM or whether you're running a specific hardware, what drivers are needed, like the environment that the system is running on. And the second one is called applets, which are the configuration options needed by the actual application at the application layer. So, here are some examples of what they would look like, right? I mean, this is not, I just threw it up there just to get an idea, but these are the config options that, some of the configuration options we've extracted in the baselet, and as you can see in the left-hand side, it's more about the hypervisor and the virtual machine. On the right side, it's more about the application libraries and so on. I mean, more details are in our paper, and I'm happy to provide like a pointer to our Git repo and stuff. So how do we track these configuration options? How do you know which ones are necessary and which ones are not? So we first have an offline phase where we track the options using multiple executions of the target application, and we trace the program counters on an application. So the reason is what we want to do is we want to take the program counters and we want to map it to source code. So we want to actually correlate down to the actual lines of code that are being enumerated by the application of a configuration option. So for this, we use QEMU, which is an open source emulator and virtualizer that allows us to trace the kernel code in a fine-grained fashion. If you have learnable kernel modules, they require additional handling. So we just need to know which kernel modules you want to test, and then we can load them, and then we can do the same tracing, but we just need a little bit of extra information. So the baselets and applets are generated during this tracing process. And we use what is known as a landmark program, which during the tracing process, the tracing starts before, at the start of the boot. And we want to know when the boot phase is done. So we put this landmark program, which tells us when the boot phase is done, so we can figure out what is happening before and after. And COZART then filters out all the hardware and environment, related options and puts them in the baselets. Everything else is there, and the boot, how we do that is using boot observations of the boot phase, we correlate it with source code in the arch or drivers or the system folders. And then the remaining options are essentially the applets, whatever the application needs. To build the kernel, we use the build systems for the kernel. And for instance, I'll use Linux as an example, but we've done it for other systems as well. So we use kbuild, and based on the configlets, we then build a debloated kernel using the existing kernel build system. We don't come up with anything new. So we want to reuse existing tools and frameworks as much as possible. And COZART can be optimized by incremental build. So for instance, you build a debloated kernel at one point, and then later on your application requirements change or your configurations change. Then you can just rebuild only those modules with which have the changes, and you don't need to rebuild the whole thing. So it kind of helps, this fast deployment and changing environments from that regard. How does it work, right? So any questions, anything so far before I go dive into the details of how it works? Okay, I'll just keep going. Feel free to interrupt, like I said. So we take the source files, the kernel source files, and we have the vanilla kernel that we want to debloat. Then we also need, like I said, we need actual application workloads. If you have a certain application, the designer of an application or somebody who uses it, you have a pretty good idea what kind of workloads you're going to be seeing. So we need an idea of the workloads. And we then, like I said, we have a configuration tracker, which uses the QEMU platform. And then we have a tool that generates the configlets from the configurations that we've tried from the program counters and the code mapping. We generate the configlets, and we maintain a configlet database, which essentially for one environment has one baselet, right? I mean, one hardware environment or one virtual machine has pretty much just one baselet, and then we have multiple applets depending on the kind of application, one for each application. This whole process is offline. Then later on, when you want to build the kernel, what we do is we have a kernel composer tool. What it takes is it takes the source files again, and it takes information from the database, and then uses the kernel builder framework, which is, like I said, which is the kernel compilation and building framework that already exists. We just make some minor adjustments to it, and then it generates the debloated kernel using this configlet information and the original source files. And this process is online. Right? This is when you want to launch an application in the kernel for the first time. So, like I said, none of this requires us to recompile the application. None of this requires any manual intervention. It's completely automated. We use as many of the existing tool frameworks as possible. If you want to change the, you want to rebuild a new kernel or update the kernel with new configuration, you can, you just need to do this online process again if your configlet database is up to date. Okay, so that's the high-level process of how things work. Let's see how we can evaluate it and make sure that we're doing the right things. So how do we evaluate it? We want to validate the system, which is saying that we're doing the right thing. We don't want to debloat the kernel and then have the system break. We don't want applications to fail. We want to measure what the boot times are, whether we made an improvement. We want to see whether application performance has been impacted negatively, hopefully not, positively, hopefully yes. We want to see whether at runtime we have seen some benefits in terms of memory savings because there's less code that's being enumerated or launched. And we want to see what are the obvious thing, right? How much code did we reduce? So to evaluate this, we started with a variety of known very popular cloud applications, HTTPD, Nginx, PHP, Redis, MySQL, all of them. And then we decided to evaluate it using two different sets of workloads. The first is commonly available benchmarks, which the community has developed over the years to evaluate these systems. And then the official test suites, I mean, quote unquote, official test suites that these applications come with. And this is important. I mean, we have some insights that we were able to glean because we use these two different things, and I'll talk about that in a bit. So as a baseline, we used Ubuntu and also Fedora, but in this talk, I'll just discuss Ubuntu. The Fedora details are on the paper. We also used a microkernel, which is the L4 Fiasco, and we also use one of the Amazon Firecracker kernels, for micro VM. So just to show that it's not just the big monolithic kernels, it's also like different kinds of microkernels that we can and VMs that we can target. To implement it, we demonstrated this implementation on a KVM-based virtual machine running on an Intel Xeon system. It was essentially a few hundred lines of code of Python and some Bash and awk scripts. Actually, this is an older implementation details because in the last few months we've re-implemented the whole thing to make it better and more efficient and in using C++ and so on. So again, I can make the Git repo accessible. So let's get the obvious debloating results out of the way. I mean, everybody is here. Okay, I've been talking about debloating. Does it actually work? Okay. So the baseline vanilla, which is we just take the baseline Ubuntu kernel for our VM and we just build it by default. I mean, actually the Ubuntu vanilla baseline has actually more than like 10 or 15,000 kernel modules. And so to make things fair, we said, okay, we'll get rid of some of the excess stuff. We'll only care about the ones that are for our platform, right? To make the comparison fair. So it's about 5,000 kernel modules remain in a default build. And so if you look at the application-based debloating, once we do the debloating, the amount of kernel modules and static modules that are remaining are significantly reduced. So you can see reductions of static modules by like 17 to 18%. And the loadable kernel modules we remove as much as like 85, 86%. So this you can see is like a huge win. It's a huge amount of code that's no longer part of the kernel, it's no longer instantiated. And we see significant improvements in boot time. And no changes for the application performance. We see faster build times for the system because again, we're building much less code, right? And the reason, I mean, this is obvious. I mean, this is what we expect to see, and we're happy to see all of these things. Just want to say that it's significant. And one of the reasons why a lot of these numbers across applications look similar, why is it 17% and 86%, is that the numbers are actually dominated by these kernel modules, right? Two things: it's dominated by the hardware configurations if you pick, and by the kernel loadable modules. So once you reduce a lot of the hardware configurations that you no longer need, then no matter what application, especially a lot of these cloud-based applications, they use very similar pieces of the kernel. So that's why you see very similar numbers. So this is cool, right? This is great work, but to me it's not as interesting as what we learned while doing this process, which is the more interesting, like the validation results. How do you validate that the application that's running on your debloated kernel has the same behavior as the original? Because I can remove how much code I want, but how do I know that it's the same application and I'm seeing the same behavior? Well, there are two ways to do it. I can compare the outputs, right? Like I can see here's the inputs and the workloads that I'm giving. Here are the outputs, right? The official outputs generated, or like log messages, output files, whatever it is. We can compare those. We can also compare coverage. We want to see like what parts of the kernel were actually touched by that application before and after. So we want to see code coverage, and we do some profiling, and we want to make sure that these remain the same. So we use these known tools called Gcav and Gprof, which is coverage and profiling. So let's look at the coverage results that we get using Gcav. So the application, let's look at these three applications. So remember I said we use the test suites and we use the benchmarks. So for the test suites with the vanilla kernel, we can see it gets about 73% coverage of the kernel code for 1 and 54 and 69. Interestingly, even the test suites are not able to, this is a classic problem with software engineering and testing, right? I mean, you're not able to get 100% coverage, your input sets, blah, blah, right? So it's not easy even in the best of times. So, but it gives us some insights into how well our system is working. So when we look at the debloated kernel using the test suites, we see very similar numbers, which is that it's very close to the percentage of coverage that the original applications get with the vanilla kernel. There are minor differences. Again, this is just like the problems with testing, right? I mean, your input sets, the kernel has some little bit of complexity of what happens at runtime. So there are minor variations. Now, it matches closely, as I said, the debloated kernel matches closely the original vanilla kernel. And like I said, we also use benchmarks. The interesting thing about benchmarks, if you look at the percentage of the code that it actually touches for the vanilla kernel, it's abysmally low to begin with. But we're able to match it closely. Given the benchmark, we're able to say that okay, we probably touch very similar pieces of the kernel, so the behavior is similar. So this is an interesting insight that we gained from from doing our experiments, which is that benchmarks, not just for these applications, we tried a bunch of other applications. The common benchmarks, and I know this depends on the actual application, the framework and everything, sure. But for these commonly available applications that thousands of people use, right, maybe more, you can see that benchmarks are really bad at providing information about things like kernel coverage and code coverage. In fact, test suites did much better. Anyway, that was kind of, I thought it was kind of like interesting nugget that we gleaned. I mean, there are some other insights we gained, and then that's in the paper. But yeah, at the end of the day, COZART is able to match the behavior of the original and also do better in terms of performance and memory usage and boot times and so on. So any questions before we go on to multi-K?
Hey, Sibin, it's Charlie. Actually, in the dream world, if you had high granularity debloater, wouldn't your target be to have your code coverage to be 100% after the fact? Because you would run your app, yes, and you would have no code in it that wasn't being used.
Yeah, ideally, yes. But we're limited by the profiling. Okay, I mean, I'll talk about the fine-grained stuff and where we can get better coverage, but there are two things that limit us. One is where the configuration options limit us to what we can see at compile time, because we're using the compile time mechanisms. So when we look at compile time configurations, we might need to include chunks of code because they fall within a certain configuration, and not all of that code might actually be used at runtime. And the second thing is, again, we're limited by the workloads, right? If we don't know all the workloads that we're going to see, it might actually include some pieces of code that may not be necessary, but we have to include anyway. So the combination of these things prevents us from being 100% for COZART. Does that answer your question?
Yeah, it does. Is the implementation of COZART, is that all published, or are you planning on like commercializing this? Because it looks great.
Yeah, both. I mean, we have, it's published, but the early versions are published. We're actually in the process of figuring out whether we can do like a startup, and we've actually re-implemented COZART as a result of that, like to make it more better and efficient and all of that. And we're also targeting things like making it more applicable to IoT and embedded systems and edge systems and like a larger, kinds of environments.
Yeah, great. Thanks.
Yeah, thanks. Anything else? Anyone else? Okay, so let's keep going. Multi-K is a framework that actually aims to do more than just debloating, right? So, and I explain why, because a COZART, like I said, you have an application and its workload, or a couple of applications and their combined workloads, how they work together. We can create these debloated kernels. And as Charlie and others, you pointed out, like it's there's some limits. You can't get 100%. But what if you have multiple applications? And what if you want to get even more fine-grained debloating? How do you deal with this? So multi-K is a framework that tries to fix both of these issues. So multi-K looks more at kernel specialization at a finer grain visibility. So imagine you have a kernel and you have a bunch of applications running on it, vanilla kernel with applications running on it. What we want to see is that for every application, we want to see its own specialized kernel, because every application instantiates a kernel separately, differently, right? So this is the ideal scenario. The problem is, as I mentioned, if we try to do this and we try to do this aggressively, we indiscriminately reduce code, we actually cause instability of our own, and the system will crash, and it just defeats the whole purpose. So what do we do? So let me, at a very high level, the 30,000-foot level, we start from the same setup, which is applications running on a kernel. What we do is we say, okay, each application gets its own full kernel, okay? And then we mask out the kernel code and only unmask the pieces of the kernel code that application needs. So the application cannot see or touch or use any of the parts that are masked, and only can use the parts that are unmasked. I'll explain what this masking means, but at the high level, for the application, for all practical purposes, the black parts of the kernel don't exist. And this is important because if, let's say an attacker gets in and tries to access code in the masked regions, it immediately get detected or stopped. But there are some problems, right? But like I said, this is a 30,000 foot level description. Like, let's look at the details and see what the problem. I mean, it's not so simple, right? Okay. The question is, again, going back to the original one, which is, how do we find what is this necessary kernel code? The second thing is, what do I mean by masking and how do I do it? Right? It's not that simple a process. The third issue is, originally all of these things, the kernel and the applications ran on a processor, right? A multi-core processor or whatever, contemporary processor. Now I have multiple kernels and multiple applications. I want all of them to still run on the same processor. I don't want like multiple separate chips. So how do I get all of this to run on the same processor? And that's where multi-K comes in. So multi-K starts again from a vanilla kernel and an application. And we have a profiler, which is similar to the profiling and the tracing we did, but this is like runtime profiling. What it profiles the application on the kernel, again with different inputs, workloads, test suites, whatever you can find. Again, the common theme among all this is like you need to know what your workload is going to look like, right? You need to know what is going to finally run on your system. And the profiler then generates a kernel profile, which tells you which parts of the kernel are needed. And then the multi-K framework takes the application and the profile that we've generated. And what it does is it takes this application, creates a custom or masked kernel, which is just the orange part. And here's the magic, right? So here's how and this is important. This is like the cool technique that we've come up with, which allows us to do all of this and more, which is we also have a copy of the original kernel running underneath the masked kernel. We call this kernel 0, which is exactly the same image as the original kernel. And it'll become clear how we use it. But this is the magic. This is what allows us to actually do all of this. And the other important thing is, because we remember that the original kernel, these two are the same. These two images are the same. And because we started from the same image to do the profiling and everything, we also need to make sure that the masked kernel and kernel 0, as we call it, have the same memory layout, which will be the case because we're starting from the same thing and then we're just masking things out. So this is kind of like how the high level, how the framework actually operates. So let's look at a little more of the detail. Let's throw some spotlights on what makes this difficult or challenging. There are system resources that are shared, like for instance, if you want to do inter-process communication, there are kernel data structures. So you can't just indiscriminately just mask things out. If you have interrupts, when you're, if you imagine if you have a customized kernel which doesn't use networking and you've optimized or mastered the network stack, but a network interrupt arrives because the other applications are using it, what happens, right? So you need to deal with interrupts, and this is challenging because what happens if the code doesn't exist? And this is where having that kernel 0 at the bottom becomes really interesting, because that provides us cover to be able to handle all of these things, even though the application version of the specialized kernel may not have it. Okay, so let's dig a little bit more deeper to see how things work. So imagine if you're running Apache or one of the applications, Apache on a CPU. Now, every most platforms have what these registers, which are essentially page table registers, and like I said, the Intel version, it's called CR3. And what they do is they point to the page table for an application, the beginning of the page table, which tells you what is the kernel text that particular application can use, or actually all applications, right? They have a common shared kernel text, and it just points to the beginning of it. And then, you just tell the CR3 points to that and tells you for that application, okay, this is where the kernel code resides and this is where the kernel data resides. So if you want to make calls, this is this is the page that you need to access. So Apache has, points to its page tables, which tells it where the kernel text resides, right? So, but in physical memory, what we do now is, instead of making it point to the original kernel pages, we create a copy of the kernel text for Apache, and which is a copy of which is that masked kernel. Essentially, we make a copy of the kernel, we mask its the parts that the Apache doesn't need, and then create copies of the pages and then place it in a different location in physical memory. And we point the CR3 register to point to this new set of page tables. Notice that's only for the kernel text. The kernel data still points to the original kernel 0 data, because we're not masking the data, we're only masking the code. Now, if there's a context switch, which is to say another application, which has its own CR3 register pointing to the original kernel text again, same process. We make copies of the pages, we mask it, and we change the kernel text to point to its version of the specialized kernel. And similarly for other applications. And all of them still point to the original kernel data. Remember that we still have kernel 0, so that still resides in its original pages. So that's still there. What we're doing is we're just making copies of those few pages that the applications need for their specialized kernels. Okay, so this is the memory layout. This is kind of what allows us to do what we want to do. And as for the exact mechanism of how this happens, so at deployment time, we start with the original kernel, kernel 0 and its data. And usually, you want to launch an application, you have an exec we call, and that sets up the page table for, say, the Apache with its kernel. The original Apache's kernel text pointer just points to kernel 0's text, and its data points to kernel 0's data. So what we do is we hook into execv as well on top of this once Apache is launched, and then or before it's officially launched, and then Multi-K comes in and instantiates this custom kernel, right? It takes the remember that kernel, what do you call it? The thing that puts the specialized kernel together by masking things. So it creates a specialized kernel for Apache, which is smaller than the original kernel. And then it updates Apache's page table to now point to the new kernel text. The kernel data still pointing to the original kernel data. We're not touching that. So this is the actual low-level mechanism that works to make this whole, the whole magic take place. And there's a small one-time launch for the application, which is 3 milliseconds, which is in the scheme that most of these applications run for hundreds of milliseconds, maybe longer. It's nothing, and it's one time. So when you context switch back into Apache or whatever, it doesn't happen. It's only the first time when you're launching that. It's only when you're launching the application for the very first time. So the challenge then becomes, again, like from before, how do we determine which parts of the kernel are required? And what do I mean by masking the kernel? So we use tracing. Again, we use QEMU, which is we run the application with expected workloads on QEMU. We try to understand which parts of the kernel are emulated. And we can do this much more fine-grained. We can do it at the instruction or basic block level, and I'll explain that. And we can trace the kernel, exactly to see which parts are used. And we have this, mechanism we call dcut, which is dynamic cut, which uses tracing. The problem with tracing is it's not always safe. Again, it's heavily dependent on the workload, and goes back to the question, like, can you see 100% of the pieces of the kernel that are used? If you're using tracing, likely not. But if you know for the most part, then it's safe, but it comes with a caveat. And there are various granularities we've tried. You can do it all the way from a feature, like an application, like a feature, like entire system calls can be removed, or you can do like page level. You can look at feature level is like entire modules can be removed. You can look at multiple pages that can be traced or removed. System calls, individual functions, even down to the basic block, individual sequences of instructions. So you can get really fine-grained in what you can remove and what you can keep. The problem with, as we go from top to bottom, we're seeing the granularity is getting more and more fine-grained. The problem is it gets more and more unsafe because we are getting more aggressive in the amount of code that we remove. So you have to find the sweet spot for your application. So to deal with some of these problems, we said, okay, we can also do some static, like a little bit of static analysis, loose static analysis, which is looking at the system calls to maybe make the system a little bit safer, to increase the coverage a little bit. So we analyze the system calls, and basically we say, okay, what are all the system calls used by an application? This is a little easier to analyze because we can do it at compile time. We can analyze the code in the application to say, look at all the system call sites and say which ones are called, and less dependent on inputs. And then we say, okay, everything that the system call requires to run, we will keep. So this is a little coarser granularity, but it's a little safer, right? And then we can use compiler features to figure out what are the underlying functions and figure out what to keep and what to remove. So we can start with the dcut, which is dynamic tracing, and then we can expand that profile by adding more kernel functions based on this analysis. So it's not either or, we can do both. And even with this, we can get 80+ reduction in the kernel, right? It's not like we're losing a lot. So this was the high-level framework. And the profiler is where these techniques like dcut or scut or any, you can put your own profile. If you come up with a really fancy profiler that does some cool work that gives you better information tomorrow, you can just use that, right? In addition to or instead of these two. But we wanted to just analyze the two that we've developed. So the second question is, how do we mask these parts of the kernel? What do I mean by masking? It's pretty simple. We look at the unwanted kernel code and we just overwrite it with a special instruction, right? Like with a 1-byte sequence, which is, in this case, we put a 0xCC, which is like int3, which is like a software interrupt. The reason to do this interrupt is if an attacker gets in and is able to try to access code that is masked, it instantly throws an interrupt that is then caught by kernel 0 and can put a stop to whatever's going on, or at least raise an alarm or do something like take action against such behavior. It's also the case if there's a fault or something that we missed. So if there's code that we legitimately missed, then it'll throw an interrupt and we can catch it. We know when it's happening. So it's almost instantaneously caught. There's no delay in when an attacker tries to do something and when it's caught. At the very least, it's stopped, right? And interestingly, it's only stopped for that application. This is the advantage of having multiple applications with their own specialized kernels. If one application misbehaves, it's caught and we can kill that entire application and its kernel, and other applications and their kernels continue to still work. And this is why we say multi-K is like a orchestration framework that lets us, have multiple specialized kernels run together. And it's also failback mechanism when the application is accessing code that's not in the profile. So implemented this on Linux on an Intel Core i7. We use the procfs interface to identify which application is running and when to switch kernels. The QEMU emulator does the tracing, and also we implemented these two tracing mechanisms. We tried with, again, 3 different applications which are pretty popular: Apache Stream and Perf. Again, a few tens or hundreds of lines of code with some scripts and some C language code, mostly C and Python and like some other scripting languages. Again, to evaluate, we wanted to see how much of the code reduction we can achieve. Is it effective at eliminating attack possibility, like known CVEs, right? So, we looked at the CVEs and said, okay, which known CVEs we removed effectively so that they don't work anymore. We looked at the time to generate kernel profile for each application, and what is the effect on runtime performance? Is there any, right? Again, I'm not going to go into all of it. It's in the paper, but I'll talk about the more interesting ones. So if you look at the attack reduction, and we tried, again, multiple reduction methods, right? From the really fine-grained ones like basic block to symbol level to even system calls. And for Apache, as you can see, it's performs really well. We get 93% for the basic block, and even in the most conservative case, it's 82% with the system call. And with Stream, we get even better, right? 97%, 98% almost. And Perf also gets close to 96% something. So it's a huge amount. It's not 100, but it's pretty close. It's pretty darn close. And the thing is, as you go with the course of granularity, as expected, the amount of code that you can reduce decreases, but it's no slouch. It's still a significant amount of code reduction. In the worst case, it's 82, but you can get up to 87% depending on the application. Now, the second goal was to see whether we improve security, which is like, how does it improve security? So we said, okay, we looked at a bunch of CVEs that exist in Linux, and we looked at the Apache web server running with Linux. There are 23 known CVEs. dcut was able to eliminate 19 of them, right? The code that the CVE needs to execute no longer exists in 19 of them. And in scut, it's 17. And these are not the same. I mean, there's significant overlap, but there are differences too. So we get a pretty significant reduction. I mean, we're not able to do 100%, but that's, again, limited by the coverage and the how much code is. I mean, some of the code that we want to eliminate is actually necessary code for the application to execute. So we can't eliminate all CVs as a result. Runtime performance, as you can see, there's virtually zero runtime performance. And in some cases, there's a marginal like improvement as well. Like it's negligible. For all practical purposes, we don't affect the runtime performance. There are some challenges with multi-K, more so than COZART, which is, again, reliable characterization of workloads is difficult. This is common across both, but more so here because we want to do more fine-grained specialization. Like I said, we need to have the same memory layouts. We need to start from the same OS-based kernel image. It's not necessarily a challenge, but it could be depending on how you're deploying these things. The data is not specialized. So if you're looking at kernel database attacks, then we're still vulnerable to it. We're looking into how this could be mitigated, but this is definitely a challenge, right? I mean, we're only preventing code-based access attacks, which is still a significant percentage of attacks, but we're not perfect. The other thing is the kernel, the Linux kernel, and most operating system kernels, because of the complexity, there's a lot of inherent instabilities. The way threading happens, hyper-threading, or the way interrupts are handled, the way things, data structures are accessed and locks are released and so on. There are like a lot of potential points for instability that could negatively affect some of these things, right? Like for instance, during context switches, did the previous kernel release its locks correctly? Did we, for instance, we may have only unmasked the a lock access code, but we've forgotten to unmask the lock release code. What happens then? So again, it goes back to how good your tracing is, right? So we're actually working right now. Again, this is joint work with folks here at our OSU, other faculty here at OSU and students here at OSU who are looking at what are the various points of kernel instabilities, which is actually an interesting project itself, because understanding this has potential beyond just this work, right? So we're working on that right now. To summarize, they're both COZART and multi-K are specialization in debloating frameworks. They can reduce attack surfaces, pretty much have no real negative runtime overheads, and they integrate well with existing application systems like containers and so on. We've shown this works with like Docker containers, not just like regular applications. And again, I didn't talk about it here, but the details are on the paper. The differences are COZART is a little bit more systematic, more stable. We use compile time options, less reliance on runtime behavior. And multi-K improves resiliency because when you have multiple applications running, you can limit failures to a single application and maybe restart that application and kick out attackers from restart with a clean piece of code, or let's just let the application die while the rest of the system operates, right? Without even noticing anything happen. So yeah, thanks to all our collaborators at Illinois and here at Oregon State. You can go to my website and you can find a lot more information about the papers and the code and other things, or just email me and I'm happy to point you to the resources, or maybe chat with some of the other collaborators or the students, the ones who've done the actual work. So yeah, that's my talk. Thanks for your patience. I'll take any questions. Somebody mentioned something in chat.
Sibin, that was great. Can always use a debloating of the OS these days. Yeah, we have time for questions. Anybody, feel free just to speak up if you ask a question.
Hi, this is Shane Collins, and I have a question. We're building a lot of, I like the whole concepts between debloating the OS. We're building apps that are like 100 containers with Kubernetes orchestrating over a bunch of servers. Any thoughts how to apply this idea to an app like that?
Yeah, so I think right now it's focused on like a single application workload running on a single server. We are looking into how to say deploy it into say edge systems where things could have multiple versions of it running on different systems. I think we may have to, for instance, sorry, let me step back. It still comes down to how well two things. It comes down to how well you can profile your runtime behaviors, right? In that instance, and the second thing is how well you can how you can what do you call it? Deploy the system. So if you can capture the workloads and the runtime behaviors, sure, we can debloat the system. We can create specialized operating systems, but we don't right now do inter-process communication yet. So the deployment becomes a challenge. So I don't have an answer for you, an exact answer, but I think we could do on the if you say that okay, the developers or the system engineers will manage the issues with things like communication across the nodes and all of that, then on a per node basis we can do the deployment, right?
Yep.
But that seems like a pretty interesting challenge in itself.
Okay, thanks. I think you're right. It's the application profile in this case. It's just hard profile to capture because it's 100 different things working together.
Yeah.
Theory sounds good. Thanks.
See, it's like Hong, you've got your your hand raised.
Oh yeah, yes, I have one quick question. First of all, thanks for the great talks, Sibin. I really enjoyed your talk. So the whole idea that you introduced here to use software debloating for improving security, have you thought about the other way around? Like you use, adversary can exploit software debloating for actually jeopardizing, making some security risk. For example, some security modules, which is part of the application, is actually removed by software debloating process by some malicious people.
Interesting. Actually, no, we didn't think about that. So one of the caveats or assumptions is that the entity or the person or the group that's doing the debloating is trusted, and it's all offline. And let's say you're taking your application and your workloads and running it on machines that you trust and run by people you trust, right? So that actually, yeah, that's a hidden assumption I should have mentioned. But yeah, but if that's not the case, if you're doing it in a more public manner, then definitely your method actually could be adversarial. I mean, you guys always think about adversarial stuff coming from the ML side. It's pretty cool. I mean, I hadn't thought about it myself. But we have this inherent assumption that it's hard to do. But it'll be interesting. We should chat about it. That's a pretty good question, actually.
Okay, thank you very much.
And Rakesh here, who's also on the call, is one of my collaborators who worked on, especially in the multi-case side of things. Rakesh, did you have any thought about that?
Yeah, I wanted to say we didn't consider the fact that some profiling phase might be compromised and an attacker might cut the code that we need. But one of the things we did consider, and that's one of the challenges we're trying to address, is when you're profiling an application load. I think another speaker, Shane Collins, also pointed it came up. Profiling interacting applications is hard, right? Because you need to try and catch all their interactions if you want to be aggressive about debloating the kernel. Similarly, let's say you're profiling an application workload and say the authentication stuff and all don't get triggered. Like there might be security functionality that doesn't get triggered during the profiling, right? How do you make sure that you trigger these things? For example, we are working on triggering the lock, release and that lock contention code.
Yeah.
Because during a normal profiling, you might never encounter contention. Similarly, how do you ensure that you're always profiling, making sure the security functions are getting profiled? So there are some challenges that we have to deal with.
The other obvious thing that may not get triggered during profiling is exception handling, right? Which might trigger at runtime. But yeah. But it's cool. Actually, we should think about it from that perspective. We never thought of that adversary model, which was somebody deliberately introducing instabilities into the kernel during the specialization. Cool. I see others. Any questions? I know Charlie says he has one on the chat. Please go ahead.
Yeah, so if I was trying to absolutely minimize the memory consumption for an embedded application, would it be possible to use multi-K and instead of making a separate copy of the kernel, just applying that masking to kernel 0? And also when you're masking out the code by replacing the dead code with like interrupts, could you just omit the code altogether?
Yeah, so okay, there's a problem with just the reason we went with masking. Again, I didn't talk about this in the thing, but the reason we went with masking instead of just removing the code is that removing code is an extremely fraught process, because especially when you go to remove code at the instruction or very fine granularity, which if you want to get like that high 90, 97%, 100, close to 100% reduction, you need to get really fine grained and remove stuff. And that causes the system to become unstable, because imagine within a function, I'm removing chunks of code, right? And now the function, we don't know whether it works correctly or not. And we could be removing important things like masking or exception handling or security or lock management and so on. So that's why and we don't know the interdependency. The kernel, there are a lot of interdependencies. I remove a piece of code here or a function here. Hey, 10 other functions that required it fail, but we never saw that, right? Which is why we said we did two things, which is that we'll mask it and instead of removing it, which is again hard to do. How do you just cut out code? We can't just like say delete code and it won't compile. And the reason we have kernel 0 is to make sure that in case something fails, if there's a fail safe. Having said that, we could think about a situation for like embedded systems where we remove that kernel 0, and embedded systems again are extremely well profiled and much better profiled than general purpose applications. We have these embedded real-time systems where we can say we will have a very fine control on what interrupts come when, what is the exact memory layout. So when we have a lot of that information, we might be able to do a much better job. We might be able to mask much better. I'm still not comfortable saying we will just excise the code altogether, right? Maybe in some future version, if we can do it in a safe way, in an automated fashion, I don't want it to be manual, then possibly, yes. And that's why we're also like, seeing how to apply these techniques to embedded systems, because it seems like a perfect thing to do, right? Because they're space constrained, memory constrained. It would be a great fit. And definitely COZART, we're looking in that direction, and multi-K potentially. Does that answer your question? I hope.
Yeah, it does. Thanks.
Okay. Anyone else?
Yeah. Anything else, folks? Yeah, I was kind of curious. So if you let's say that this became widely used, and programmers, developers were aware of it. Do you have any sense of how much extra benefit you'd be able to provide if they were actually writing their code aware of this functionality in the background?
Yeah, actually, if they did, that would be great. Like for instance, in COZART, they could think of like maybe additional configuration options that gives us even more final control. They can put in preprocessor statements or make file statements that could help us, right? And they could say, look, I actually know that in certain instances, this code is never going to be triggered on this kind of platform, and you can put in those as configuration options. So, our system can use that to cut out even more or keep or they could tell us, look, they could put certain process statements that say, that gives more information like, hey, this is the security module. You don't want to do any cutting out here, right? Or they could say, this piece of code is the one that locks the data structure, and here is the processor configuration with the which unlocks it. So keep these two together. So there are a lot of like these hints they could actually put in by defining new options that our system would just then automatically use and make it much better. It would improve stability, but also reduce the code that we used, making it overall better. Yeah.
In addition to just maybe removing some calls and replacing them with some other calls. Yeah.
Yeah, that too, right? Like if they know that, oh, I'm going to remove, like, if like there are 2 system calls and say, okay, the 3 system calls and 2 of them use similar code, and if maybe I could just use the 2 of them and avoid the 3rd one, right? Like there are, of course, more fine-grained things that they could do, because we're still doing some tracing. We want to see like what parts of the kernel are actually touched. So the more information we can get by the application developer, the better. The other thing they could do is they know, I mean, with caveats, no offense to anybody, most of us think we mostly are the best identifiers of how our code works, right? And maybe they can also provide better workloads. They can say, you know what, this code is meant to run on this kind of a system with these kind of inputs. Sure, it works with these other kinds of input, but it works best with these kinds of inputs. And that's what we care about most. That kind of information would also be really useful.
Nice, thanks.
Yeah.
Well, I think we are at about the stopping point. So yeah, I'd like to thank you a lot, Sibin. That was very interesting.
Thanks, Alan.
It's gonna be exciting to see where that goes.
Yeah. Thanks everyone for the great questions and for your patience in sitting through the talk.
Yeah, so we'll be back in 2 weeks with another one of our new faculty. So we'll see you then. Thanks, everybody.
Thanks. Bye.